Hey, college physics students, coming at you from my basement, which is our classroom for this year, this summer. This is chapter 3. We'll start on chapter 3 today. Uh, Hope you're all staying healthy, safe. This semester is going to be hard enough without somebody, one of you or me, getting sick. That would be really bad. So, no kissing, no touching your face. And let's go. Back to physics. Well, we don't want that. That's what infinity looks like. Um, chapter 3. Chapter 3 is a combination of chapters 1 and 2. In chapter 1, we learned about vectors, x and y components. That's going to be important in this chapter. And in chapter 2, we learned about position, velocity, and position, velocity, and acceleration and time, describing motion, and that's going to be important also. They're going to combine in a way because what we're going to do is have a set of equations like we did in chapter 2, except we're going to have one set for the x direction, the x components of vectors, and one set for the y direction. The x and y direction are independent. One happens, they happen simultaneously. I'll put it that way. Okay, so the first thing we did in chapter 2 was describe displacement, the initial position, final position. Well, you can see from this picture here that those are vectors now in 2 dimensions. Obviously, we live in 3 dimensions. The extension to 3-dimensional motion is pretty clear, pretty obvious, but we won't do that. We'll probably stick to just 2-dimensional motion, won't go to 3. Okay, so we have an initial and final position and a displacement. And then what we defined after that was the average speed, which was a displacement over the time. And now that's going to be a vector divided by a scalar. Time doesn't have a direction, but this vector does. And the instantaneous velocity, the average velocity, is going to be the average velocity over a long time period. We're going to define the instantaneous velocity, and that is equal to this is the average velocity, which is a vector. Wow, lots of stuff there. We're going to define the instantaneous velocity. I don't know if they defined it in these notes. That's equal to delta r, which is a vector, divided by delta t as delta t very small. So the instantaneous velocity is just the average velocity over a very small time interval at that moment. So that's how fast, that's our velocity at a particular moment. It has a magnitude and a direction. So the direction of motion is the direction of the velocity. So this is the direction of motion, whatever that direction is. That's the direction we're moving at a particular instant. Let's go back and look at this picture. See, this car is moving on a track like this, and its average velocity between these 2 time intervals is this vector here divided by so its average velocity is this way. Notice that that's not the direction of the motion of this car. The instantaneous velocity, which I'll just call v, the instantaneous velocity is going to be tangent to this circle at every point. So the instantaneous velocity at this point is in that direction. The instantaneous, get that stuff out of here. The instantaneous velocity at this point is going to be in this direction. The instantaneous velocity when it's right here is going to be in this direction. So the instantaneous velocity, even though this thing might be moving at a constant speed, the instantaneous velocity is changing direction. This guy is basically making a left turn continuously. He's just continuously turning to the left. Okay. Okay, if we have an instantaneous velocity, we can now define an acceleration vector, an average acceleration vector. That's equal to the change in the instantaneous velocity, whatever direction that's in, and divided by the time. Okay, now let's step back to Chapter 2 for a minute. Here's our four nice equations. One form of them anyway. Here's a whole, we got them over and over again here. Oh yeah, well. Okay, so here's from Chapter 2. Here's the VVAT equation. Here's the X equation. Here's the V squared equation. And here's the last equation. Basically, we're going to define these velocity, acceleration, and position in terms of the x and y components of those vectors, because vectors are easier to deal with when you're thinking about their x direction parts and their y direction parts separately. And that's what we're going to do here. So when we put a little subscript on here, like we did in Chapter 1, that means it's the component of the velocity vector in the x direction. This is the component of the velocity, the initial velocity vector in the x direction. And this is the component of the acceleration vector in the x direction. Now these are all just numbers. They don't have any direction, so they're all directed in the same direction, namely x. They can be positive or negative. They can be to the right on the x-axis or to the left on the x-axis. And here is the x component of the position vector. That's going to be what we just call the x-coordinate. And this is the initial velocity in the x direction. This is the acceleration in the x direction. So here we have the same equations. We could actually we could extend this further, right? We could say well, we could say we got another equation here. We could write that the velocity in the x direction squared, is equal to the initial velocity in the x direction squared plus 2 times the acceleration in the x direction times the x position. Here we're assuming that the initial x position is equal to 0. Remember, in Chapter 2, unless there is a compelling reason to do otherwise, we always set the initial x position to be what we're calling position 0. In this chapter, there's not going to be any compelling reasons to choose otherwise. So they usually, with these equations, in 2 dimensions, they set the initial position in the x direction equal to 0. We're going to set the initial position in the y direction equal to 0 also. So basically, we're putting the origin of our 2-dimensional xy plane at the position where the object starts. Okay, and then we could write this last equation too. The x position is equal to 1/2 the initial x velocity plus the x velocity at some time times the time. Okay, so there we go. Here's those. Oh, there they are right there. So they were in the notes here. Okay, and then likewise in the y direction, we have 4 equations. The equations of Chapter 2, just written in the y direction. Okay, what is this initial velocity in the y direction and initial velocity in the x direction? Well, we get that back from Chapter 1. Here's our initial velocity vector. It's the way the object is, the direction the object's moving and how fast it's going at the start of this motion. And the So we might call the magnitude of the initial velocity the speed. How many meters per second is it going at the initial instant? The angle with the x-axis, once again, like in Chapter 1, the angle is the direction that this object is moving at the starting time. And then if we want to know the initial velocity in the x direction, we just have to dig out an equation from Chapter 1. The initial velocity in the x direction is the initial speed, which I'll write this way. Normally people just write this as v0 without a vector sign on it and without the magnitude sign. That's the initial speed. They just write it as v0 times the cosine of theta. Remember, to find the x component of a vector, we take the magnitude times the cosine. So most of you have already guessed the initial velocity in the y direction is equal to the initial speed times the sine of the initial angle. Okay. Now let's see if we can apply this. So the strategy for these problems is frequently similar to the strategy in Chapter 2. We compile a table or a list of the things that are given to us and the things that we're looking for. And then we try to find equations from those 8 equations that I just described. We try to find equations that will answer our questions. So, a moving spacecraft. In the x direction, the spacecraft has an initial velocity of 22 meters per second. Okay, that's v0x. Because it's an initial velocity and it's in the x direction. And it has an acceleration of 24 meters per second squared. That's a sub x, because that's an acceleration and it's in the x direction. In the y direction, the analogous quantities are 14, so that's the initial velocity in the y direction, and it has an acceleration of this. At a time t equals 7 seconds, well, time is the same in the x and y direction, because these x and y motions are taking place simultaneously. Okay, so we're supposed to find its x position, and its x velocity, its y position, and its y velocity when t is equal to 7 seconds. And then the final velocity of the spacecraft. That's going to be a vector. It's going to be moving in a particular direction with a particular speed. So we're going to find all those things. All right, so let's, x is what here they've done it for us. X is what we're looking for. Here's the acceleration in the x direction. Vx is what we're also looking for. Here's the initial velocity in the x direction, and here's the time. So, and likewise for y. So I'm going to do this problem in 2 parts. I'm going to do it for the x direction first. And I'm going to find this first, Vx, because that's the VVAT equation, and that's easier. Vx is equal to V0x, which is 22 meters per second, plus the acceleration, which is 24 meters per second squared, times the time, which is 7 seconds. Okay, I'm not going to do all this arithmetic. You're certainly capable of plugging that into your calculator. I want to find then the x position, and I would take V0x that's V0x times t, which is 7 seconds, plus 1/2 a sub x, which is 24 meters per second squared, times the time squared, which is 7 seconds squared. Once again, you're capable of cranking those numbers out. We don't need to use up class time for that. Then I do the same thing in the y direction. We're using y instead of x for the position in the y direction. So v sub y would equal, well, what's v0y? 14 meters per second. plus the acceleration, which is 12 meters per second squared, times the time, which is 7 seconds. Once again, you can chunk that number out. The y position of the spacecraft is going to be v0 y, 14 meters per second, times t, which is 7 seconds. You might have to look back at these equations. They would be on an equation sheet. Certainly it will be acceptable during a test. I don't know whether I'm going to have you make your own equation sheet yet, or whether I'll probably provide an equation sheet with the exam. It'll be, when you go to the exam, it will be there. But if you want to have your own, it's not going to bother me. You could have a piece of paper while you're on your table while you're taking the test. That's an equation sheet that you made up. And then you'd have plus 1/2 AT squared. So I don't need to look back at the equations. I've been doing this a long time. So it's 1/2 times 12 meters per second squared times 7 seconds squared. Once again, you can chunk that number out. That would answer part A, I believe. Now it answers part A and B. Then we're supposed to find the final velocity of the, so part C, this is part A, this is part B. Part C of this is to find the final velocity. Well, you already did that. You found the y component and the x component of the final velocity at 7 seconds. But usually they want this expressed as a speed and direction. Speed and direction. Well, how do I find the speed? That's the magnitude of the velocity vector. So I'm just going to write it like this. A lot of times people get sloppy about how they describe the speed or the magnitude of a vector, especially when they're just writing like this. I would have to take the square root, like I did back in Chapter 1, of the x component squared plus the y component squared. Once again, so you need the answer to part A for this, the answer to part B for this. And then I'd find the direction that this spacecraft is moving as the arctangent, or the inverse tangent, of the y component of the speed over the x component of the speed. Remember, the direction of the velocity vector is the direction that the object is moving. And this object's moving in a different direction at every instant. Every instant it has a different x component of velocity and a different y component of velocity. Okay. The most common example, especially in day-to-day life, of two-dimensional motion is projectile motion. That's a motion that's like free fall in 2 dimensions. Remember, free fall was the motion of an object that's being acted on only by gravity. It means gravity is constantly accelerating it downward at every moment. So let me give you an example. Here's something. I don't know whether you can see this or not. I don't have a view of what my camera looks like. But once that pen left my hand, you've thrown things in like that throughout your life. You know what happened. Once that pen left my hand, it followed a curved path and landed on the floor over there. And after it left my hand, from that moment on until it hit the floor, till right before it hit the floor, it was being acted on by just gravity. Air resistance too, but air resistance on that pen was not very powerful. So we can neglect air resistance for the motion of most items if they're heavy enough. So, because it depends on whether the air resistance is You really need to get to chapter 4 for that. Depends whether the air resistance is very small compared to the weight of the object. And for that pen, that was true. For a light piece of paper or something, maybe not. And it also depends how fast it's going. The faster it goes, the bigger air resistance gets, and eventually the air resistance at some speed, the air resistance will take over from the weight. Anyway, neglecting air resistance. That object was moving under the influence of gravity, which is always accelerating it, just like in Chapter 2, at 9.8 meters per second squared downward. There's no acceleration of gravity in the horizontal direction. So here's the, let's just do a little note here. Here's the pen. It left my hand with some initial speed at some angle, and then the pen went like this. This is a combination of, this pen was moving with two kinds of motion. In the y direction, it was going up to some highest point and then falling back down, just like objects did in the upward direction if I toss them up in Chapter 2. In the horizontal direction, the object was moving at a constant, steady speed because gravity wasn't accelerating or changing the speed in the horizontal direction. So that's called projectile motion. It's free fall in 2 dimensions. And it's the motion of a cannonball. When you launch a cannon, once the cannonball leaves the cannon, it's being acted on only by gravity from that moment on until it hits the ground. Then once it hits the ground, then it's being acted on by the ground and gravity. So these equations only work from the moment after it leaves the object, the thing that launched it, to right before it hits the ground. So we're going to have a set of equations that are very much like the equations that we just used, except the acceleration in the x direction for projectile motion is always going to be 0. And the acceleration in the y direction for projectile motion is always going to be minus 9.8 meters per second squared. So I'm going to call that minus g. G is the number 9.8 meters per second squared. For these problems, we always assume the downward direction is negative. That's an arbitrary assumption, but that's the assumption everybody always makes. All right. So what are they asking us here? The airplane is moving horizontally with a velocity of 115 meters per second at an altitude of 1050 meters. Determine the time required for the care package to hit the ground. Okay, so as soon as this plane releases this package, at that moment the package is also moving horizontally at 115 meters per second because it was on the airplane. But it's only going to be moving horizontally for a moment because it's immediately going to start falling. So we want to determine the time here. So here's the ground. The ground is going to be 1,050 meters below the starting point. Remember, we always call this x0, the initial position, y0 equals 0. Remember, our equations made that assumption from the beginning. So the y-coordinate of the ground is negative 1050. The acceleration in the y direction is minus 9.8 meters per second squared. What's the velocity in the y direction when it hits the ground? I don't know. And what's the initial velocity in the y direction? That's 0 because the initial velocity is horizontal. Theta is equal to 0. And v0x will be 115 meters per second times the cosine of 0. The cosine of 0 is 1. So v0x is, this initial velocity is totally in the x direction. I didn't need my equation to do that. I can just look at it. The initial velocity in the y direction is equal to 0 in this problem. That's equal to 115 meters per second times the sine of 0. Well, the sine of 0 is 0. And the time is what I'm looking for. In the x direction, we don't know what the x coordinate is when it hit the ground. I don't know if we're being asked that. No, we're not. But you probably would be. Like, what is the x position when this thing hits the ground? How far did it move in this direction from the time it was dropped? That would be an important thing to know if you wanted to catch this package, or you wanted to if the person in the airplane wanted to know when to drop the package so that this person would catch it, or then that would be an important thing to know. They don't ask us here. Oh, yes, they do. They want to know the velocity of the care package when it hit the ground. No, they don't. They're not asking for the position, but unless it's on the next page. No. But we're going to find it anyway. We're going to find the x coordinate, how far the package moved horizontally during its fall. And the acceleration in the x direction, since gravity doesn't act in the x direction, is 0. The velocity in the x direction, we don't know. And the initial velocity in the x direction is 115 meters per second. And we don't know the time either. Okay, so let's take a look at the y equations first. Y equals v0y times t minus, that's coming from the fact that the acceleration is negative 9.8 meters per second squared. So that's frequently written like this. So this is an equation for the y direction for projectile motion. We're going to use this because we know that this is negative 1050 meters. We know that this is equal to 0. That's nice. And we know that negative 1/2 g is negative 4.9. Half of 9.8 is 4.9. Comes up frequently. So this equation only has an unknown of time. And that's what we're being asked for. So cool. So I'm going to divide both sides by 4.9 and take the square root. So I'm going to get, the negative signs would go away, of course. I'm going to find out what this is for grins. So I'm going to grab my calculator here. There it is. Turn it on. And just take 1/0 square root. Second square root 1050, if I remember that number right, divided by 4.9. And I get 14.64 seconds. So now I know the time in both of these. For both of these lists, it's 14.64 seconds. And this is 14.64 seconds. Okay, I think that was part A. The velocity of the care package, this is not stated very well. They mean what's the velocity when it lands? Well, its velocity in the x direction, I know that right off the top of my head. It's 115 meters per second because the velocity in the x direction never changes until it hits the ground. And the velocity in the y direction, I'm going to use the VVAT equation. That's an initial velocity in the y direction plus the acceleration in the y direction times the time. Well, the acceleration in the y direction is negative g. So this equation for projectile motion is usually written like this. V sub y equals the initial velocity in the y direction minus 9.8 times t. Well, I know what time it is now. It hits the ground at 14, well, let's make it 14.7 seconds. So the velocity in the y direction is equal to the initial velocity in the y direction, which is nothing, and minus 9.8 meters per second squared times t, which is, I forgot already, 14.7 seconds. This is going to be negative. It's moving downward when it gets to the ground. So I'm going to figure out what this is. 9.8 times 14.7. 9.8 times 14.7. And I get 144.06. So it's actually moving faster in the y direction when it got to the ground than it was in the x direction. So I get negative 144 meters per second. So find the final velocity of the care package. The final speed, which is what they're talking about here, is the square root of the x component squared plus the y component squared. Notice I don't care about this negative sign here because I'm going to square it. And let's find out what that is. Square root of 115 squared, there's my x squared button, plus 144 squared. And I get that it's moving 184 meters per second. And what direction is it going in? Trusty formula from Chapter 1. It's the angle that has a tangent, or the untangent, of the y component, which the negative sign matters here, so I got to put it in there, over the x component, which is 115. So I take the inverse tangent of negative, there's a negative sign on this calculator, 144 divided by 115. And I get, it's in radians. Remember, this calculator resets itself every time. So I got to go down and change it to degrees if I'm going to do any inverse. Go back to the home screen, just press it again. And I get minus 51.4 degrees. So when it hits the ground, the package is moving in this direction at minus 51 degrees. This is minus 51 degrees. Makes sense. It's what I'd be expecting, I think. All right. A conceptual example. Suppose you're driving a convertible with the top down. The car is moving to the right at a constant speed, and you point a rifle straight up into the air and fire it. In the absence of air resistance, where would the bullet land? Behind you, ahead of you, or in the barrel of the rifle? I'm going to let you think about that. The height of a kickoff. Okay, well, projectile motion takes place a lot in sports. And this is an example of a baseball. Once it leaves the bat, when it's hit, follows the path of, ignoring air resistance, follows a parabolic. This, by the way, is the shape of a parabola, this path. If you were to graph x and y as a function of time for those equations that we just had, you'd find a parabola. We're not going to worry about the equation for that parabola. It can be derived, but I don't think we're going to use it. A place kicker kicks Okay, so a batted ball, once it leaves the bat, until it's caught or hits the ground, it's being acted on by gravity alone. And so that determines its path through space. Gravity does. Kicked football, thrown footballs, pitched baseballs, thrown baseballs. Anytime you throw something, from the moment it leaves your hand till the moment it comes in contact with something else, uh, as long as air resistance is negligible, it's going to follow that same path. Very common in everyday life. So we have a place kicker. He kicks a football at an angle of 40 degrees. So they're telling us that this is 40 degrees. And the speed of the ball when he kicks it is 22 meters per second. That's not a really great speed for a kickoff. It reaches some maximum height here. Once it leaves his foot, gravity is doing its thing here. What's gravity doing? Gravity is slowing it down in the vertical direction, stopping it, and then speeding it up back down. And in the horizontal direction, gravity is not doing anything. The ball just continues with its same horizontal speed. So V0x and V0y, I'll worry about this, the question here later. I'm going to calculate the initial velocity in the x direction and the initial velocity in the y direction because that enters into our problems. It's just the magnitude of the initial speed, 22 meters per second, times the cosine of 40 degrees. And V0y is 22 meters per second times the sine of 40 degrees. So that's just two numbers. I'm going to find them. Easy enough. Get my calculator. Oh, I shut my calculator. Turn it on. Remember, it reset. So I better go to the mode button and change to degrees here. And then go back to the home screen. And now I'm going to take 22 times the cosine of 40. And I get 16.85 meters per second. That's how fast it's initially kicked in the x horizontal direction. Then I'm going to take 22 times the sine of 40 to find out how fast it was kicked in the y direction. 14.14 meters per second. Easy enough. Okay, here. They're using 14 and 17. Okay. I'll buy that. So, y, so they're talking about the y direction here. Why are they talking about the y direction? Determine the maximum height that the ball attains. Okay. Here's something very important about projectile motion. The velocity, when its maximum height, is the moment that it turns around in the vertical direction, up here. Oh, you can't see that because my calculator. Let's get my calculator out of there. The maximum height is where it turns around. Here's where the ball was going up before this, and it's going down after it. So at the maximum height, and this is something everybody knows about projectile motion, at the maximum height, the velocity in the y direction is 0. That doesn't mean the object's still there because it's going still in the x direction with the same starting speed that it had. But it's not going up or down at that moment. It's turning around. So the velocity in the y direction is equal to 0 at highest point. We don't know the time here. They don't tell us what time it gets up there. Now, there's two ways we can solve this problem. I could use the VVAT equation, Vy equals V0y minus GT. I could use this to find the time. And then I could use y equals V0y minus 1/2 V0y times t, minus 1/2 GT squared to find y. That would be one way. But I could also use this equation, Vy squared equals V0y squared minus 2g, that's the acceleration, times y. I could use this equation, and it doesn't have any time in it. Remember, that's our equation from Chapter 2 that contained no time. We've used it frequently. And I know that the velocity at the top is equal to 0. And I know the initial velocity in the y direction is equal to 14 meters per second. I'm going to write that. And I know that 2g is equal to 19.6. So I know that this is minus 19.6 times y. 2 times 9.8 is 19.6. 1/2 times 9.8 is 4.9. Little arithmetic trivia. So I get that the highest point is 14 squared over 19.6 meters. That would take care of that. Usually what you really want to know is like how far did this kick go and how long was it in the air? Well, here's something that might be clear to some of you. It takes the same amount of time for it to get to the highest point as it does for it to fall back down to the same level. So whatever the time is over here on this half, it's the same amount of time over here. So if I wanted to find the hang time, I guess I would go back to this equation here and find out how much time it took to get to the highest point. And then the amount of time it takes for the whole flight is twice that. So I'm going to find the amount of time it takes to get to the highest point and multiply it by 2. I'll use the VVAT equation for that. Vy equals V0y minus 9.8 times t, minus gt. So this is equal to 0. V0y is 14 meters per second, minus 9.8 meters per second squared, times t. Adding this to both sides of the equation, getting it to the other side, then dividing by 9.8. I'm going to do all that algebra in one fell swoop. I would get 14 over 9.8 seconds. This is going to be time to the highest point. That's not the hang time. That's half of the hang time. Okay, 14 over 9.8. Grab my contraption. 14, oh, turn it on. 14 divided by 9.8. 1.43 seconds to get to the highest point. So the hang time is 2 times 1.43 seconds. I don't need my calculator for that. That's going to be 2.86 seconds. That's probably a pretty reasonable hang time. What is the range of the projectile? Range is a a term we use for how far horizontally a projectile goes. So that's equal to x. X is equal to v0x times t plus 1/2 a sub x times t squared. But for projectile motion, a sub x is 0. So in the projectile motion equations, that term doesn't show up. And I just need the initial velocity in the x direction. I found that way back on the first page here. The initial velocity in the x direction is 17. They're calling that 17. Here we go. So this is just 17 meters per second. And the hang time, that's the time it takes for this x to happen, is 2.86 seconds. Well, whatever that is. I'm not going to drag my calculator out for that. Okay, here's a conceptual example. Two ways to throw a stone. I'll work on a picture of this. I'm going to leave this conceptual example for you to think about. Two ways to throw a stone from the top of a cliff. Well, there's an infinite number of ways to throw a stone. But a person throws two stones. The stones have identical initial speeds, but stone 1 is thrown downward at an angle, and stone 2 is thrown at the same angle, downward at some angle. No, this is pretty bad. This is thrown upward at some angle above the horizontal, and stone 2 is thrown at the same angle below the horizontal. So this is not stated very well. Neglecting it, which stone, if either, strikes the water with greater velocity? All right, so here's the cliff. Here's the person. He throws one stone upward at some initial speed, and the stone goes and hits the water. And he throws another stone downward at the same angle, and it goes. Which one hits with greater velocity? What's this? Let's look at this stone that's being thrown upward. It rises to some highest point, and then it starts to fall. And once it gets over here, its velocity in the y direction has reversed. It's gone up and come back down. So once it gets right here, it's moving the same speed as this guy was initially. And then it's going to follow the same path and get down here, just like this one did. So I say they're going to hit with the same speed. They're not going to hit at the same time. I can see that. This one's going to hit way before this one does if you threw them at the same time. But that would be what I'd think about that conceptual problem. Okay, relative velocity. Let me just talk about relative velocity for a second. Suppose I have a car here, and it's a convertible, so there's a hole on top. And I have a guy with his head out of this convertible. And the car is moving with some speed, v car. And this guy pitches a baseball. Here's a baseball. With some speed, v ball. So he's a professional pitcher. He throws it 90 miles an hour. The car is driving along hazardly at about 60 miles per hour. And now we have a batter here. Here's a batter standing on the ground. And he's holding a bat, a baseball bat. Uh, what does he see that ball coming at him? What speed does he see the ball? Well, I think you might believe that, well, the car is moving 60 miles an hour. Then he threw the ball at 90 miles an hour. This poor batter here is going to see this ball coming at him at 150 miles per hour, and he's probably not going to hit it. Um, so this is an example of velocity addition when you have relative velocities, and there's a pattern here. This is the velocity of the ball with respect to the ground. The velocity of the ball with respect to the ground. That's equal to the velocity. This is the velocity of the ball with respect to the car, because it's this guy throws 90 miles per hour from his standing position, and his standing position is in the car. So this is the velocity of the ball with respect to the car, plus the velocity of the car with respect to the ground. That's what this is. This is 60 miles per hour. If this guy looks at the car, it's coming at him at 60 miles an hour. So you see there's a pattern here. The velocity of the ball with respect to the ground is the velocity of the ball with respect to the car plus the velocity of the car with respect to the ground. See, these two here are the same as these. These are called frames of reference. So the car is one frame of reference. The ground is another frame of reference. So this is the velocity of the ball with BG, and that's what occurs here at the end. The car is an intermediary between the ball and the ground. Okay, so that's the equation that they arrive at right here. The velocity of the, I don't know, I can't hardly read this, ground person. Okay, here's a person that's walking on a train, and he's walking at 2 meters per second. The train is moving at 9 meters per second, and this guy is watching him walk down the train. So he sees him moving at 2 meters per second plus 9 meters per second. Okay, so that's a very similar description there. I like the baseball and the car better. So you see that these two frames of reference, or these two velocities, are the same as these two, and the train is the intermediary in that case. So this is true for vectors also. Those were just motion along a straight line, but it's true for vectors. The engine of a boat drives across a river that is 1,800 meters wide. The velocity of the boat relative to the water is 4 meters per second, directed perpendicular to the current. The velocity of the water relative to the shore is 2 meters per second. What is the velocity of the boat relative to the shore? Okay, so what's the intermediate thing here? The intermediate thing here is the water. The water is flowing this way in the x direction. The boat is moving in the y direction. It's trying to go perpendicular to the current. The shores are here and here. These are the shores. So the velocity of the boat relative to the shore. The velocity of the boat relative to the shore, it's a vector, is equal to the velocity of the boat relative to the water. That's one of the things they gave us, plus the velocity of the water with respect to the shore. That's the current. This is the current. Okay, so let's do it. This is a vector addition problem from back in chapter 1. So the velocity of the boat relative to the water. So that's in the y direction. This is totally in the y direction. And let me see. It's moving 4 meters per second, directed perpendicular to the current. So this is 4 meters per second in the y direction. Remember, that was a symbol J, I think, the book uses. And the velocity of the water with respect to the shore, that's in the x direction, according to this picture. Here's the x direction, here's the y direction. And so that's equal to 2 meters per second in the x direction. I think that's called the I hat direction in this book. So anyway, just let's look at a picture. That's 2 meters per second in the x direction, and it's being added to 4 meters per second in the y direction. So the velocity of the boat relative to the shore, this is the velocity that a person standing on the shore here sees the boat moving. He sees the boat moving at a speed of the square root of 4 squared plus 2 squared meters per second. And he sees it moving at an angle of the arctangent, inverse tangent, of 4 over 2. So that's how fast it's going. And what direction it's moving. That's the direction that the boat's moving with respect to the shore. So the boat, even though this guy is aiming straight across the lake here, the boat's following a path like this. And whatever the inverse tangent is of 2, 4 over 2. And he's moving at this speed. The time it takes, there's a lot of ways you can figure out. This is just a right triangle here. You know that this this river is what? You know that this river is 1,800 meters wide. And you know this angle right here. So you can find this distance. The distance that the boat moves divided by the speed. Or you could just take for the time the distance it moves in the x direction or in the y direction divided by the time, which is divided by the velocity, excuse me, which is 4 meters per second in the y direction. And that would be 900 over 2. 900 over 2, 450 seconds. I think that's the last topic in this chapter. So I'll see you in chapter 4.